In this presentation I will continue the discussion on how to use Prony's method to determine the mode parameters from a digital filter perspective. So in particular we will discuss Padé's and Shank's methods. So from an earlier presentation we know that the process of mode parameter estimation from a vibrating mechanical structure can be viewed as a digital filter synthesis problem. So we actually have to find the denominator coefficients and the nominator coefficients for a filter, a digital filter that has this transfer function. So when the filter is fed with our exciting force sequence, we should find the coefficients, denominator coefficients and nominator coefficients that makes the filter response sequence xn fit our mechanical system's response sequence as closely as possible. That is what we have to find. That is our mission. So, from another presentation we know that Prony's method, when we use the modified residual, will give us a linear equation for the denominator coefficients a, n. And if we write this linear system of equations in a matrix vector form, we find that the system matrix is built up from our sampled versions of the system impulse response function. And the system impulse response function we can calculate from our measured frequency response functions. The vector A here is our the denominator filter coefficients, and the right hand side vector is also built up from the system's measured impulse response function. So from a sampled version of the system's impulse response function we can determine the denominator filter coefficients. And as you can see here, since we have p unknowns, this matrix contains p columns. So the question now is how and what elements should we put in the rows? And well, in order to be able to solve this equation in a good way. Because when we have solved this equation and obtained the denominator filter coefficients, we can use a recurrence relation to determine the nominator coefficients. So you see, the recurrence relation contains the measured impulse response functions and the denominator coefficients. So, how to build this linear system equations for the denominator coefficients? Well, one alternative, the most simple alternative, is to use Padé's approximation. Padé's approximation means that you use exactly p equations to determine the p unknown denominator coefficients. So that means that the system equations looks like this. We have now p rows and p columns. So this system has a unique solution. Of course, if the impulse response function is, if we do this measurement over a sufficiently long time so that we can get samples in the impulse response functions that vary sufficiently much. So this is Padé's approximation, and you can simply solve this as you solve an ordinary linear system of equations. And when you have solved it, you can use this recurrence relation for the nominator coefficients. And as you can see here, since you will have to use sampled impulse response functions from index 0 to q plus p. This means that you need p plus q plus 1 sampled values of the impulse response function. If you have that, then you can solve this problem, in principle at least. Well, one problem now is that Padé's approximation is sensitive to disturbances. If you have measurement errors, noise, or something that makes your measured input data inaccurate, then the solution here, the denominator coefficients, will not be quite correct. You will have an error in it. And in order to make this method more insensitive to disturbances, Shank used the approximation that he used more equations, more data, to determine these unknown denominator coefficients. And that gives us then an overdetermined system, which is hopefully then less sensitive to disturbances. So in this case, we use, for instance, p plus m equations. So the system now reads like this. So we have p plus m rows for the p unknown denominator coefficients. So we have an overdetermined system now. And we want, well, if we formulate it in a more shorter, well, a more compact way, we have the system matrix that is built up from these measured samples of the impulse response function and the unknown coefficient vector A and the right-hand side vector, which also consists of sampled impulse response function data. So our task now is to solve this in an optimum way. And how do you do that? Well, the standard method to solve overdetermined system in the least squares sense, that is, to find an optimum solution with a minimum least squares error. That is to solve the normal equation, that is to multiply the system matrix from the left side with its own transpose. So this is a transposed system matrix. So multiply the equation from the left-hand side with this. Then the new linear system will read like this. And this is now, of course, a p by p matrix. So this has a unique solution. And the solution will be the best possible solution in the least squares sense. So when this system is solved, you can, you solve it like this, that you simply, if you have it in the computer form, if you can calculate the inverse of this matrix, then you multiply from the left with the inverse of the matrix. Any suitable method to solve a linear system equations can be used. And when you have the solution, and you have solved for the coefficients for the denominator coefficients A, then of course you use the recurrence relation to calculate the nominator coefficients. And when the denominator and nominator polynomials are known, then you can of course calculate the system poles, which is one set of the mode parameters that we're looking for. And that is simply the zeros of the denominator polynomial p. And you can also calculate the mode shape component that corresponds to the frequency response function that you are analyzing by calculating the transfer function residues. That is, if you formulate the transfer function as the ratio of the nominator and denominator polynomials, you make a Laurent series expansion, and the residues are then the denominators in each term of this Laurent series, as we have discussed in an earlier presentation.